No, yeah, please.
Okay, 1 second because I cannot see my cursor. Good. Yeah. So thank you very much, Yohei, for the nice introduction, and thank you very much for the invitation and the chance to be there at Minnesota, even if remotely, and talk to you about some of the research that I've been doing in the past. For some reason, I cannot see my cursor, so I think it's going to be easier if I share directly from preview. Yeah, okay. Sorry about that, but this way I can point in the slides. Okay, so as I said, thank you very much for the invitation, and I would also like to encourage you to ask questions during the talk if you want. So no need to wait till the end, or if you prefer, you can also wait till the end, of course. But feel free to interrupt me at any point. So today I'm going to be talking about the strange physics of dark baryons. And you will see what I mean by strange physics. It's nothing too strange, but just is the physics of dark baryons as they interact with hadrons containing strange quarks. So this is mostly based in this paper over here with Gili Elor, Miguel Escudero, Bartos, Fornal, Ben Greenstein, and Jorge Martin Camales. So let me start with a bit of motivation. The motivation is that the universe is something that doesn't quite look how a particle physicist would expect, because based on the standard model, we would think that the universe should just be filled with neutrinos and photons in roughly these proportions that I show here. But this is nothing like we actually see when we go out and look. So we see that there is a lot of dark energy, dark matter, and baryons. So these things are calling for an explanation within the particle physics framework. So I'm going to focus today on two main outstanding open questions, which are the particle physics origin of the matter-antimatter asymmetry and the particle nature, and also of the origin of the dark matter that we see in the universe. And I'm going to argue that there are some interesting phenomenological and theoretical scenarios in which these two, the origin of the matter-antimatter asymmetry and of the dark matter, could be connected. So let me start by briefly introducing what baryogenesis is. So baryogenesis essentially is a field that tries to explain this very one number, the baryon asymmetry of the universe, which is just the excess in the number of baryons over anti-baryons, and it's usually normalized by the entropy density of the universe, or essentially the number of photons in the universe. So we observe this number to be tiny, but importantly non-zero. So essentially we see that there is an extra baryon per anti-baryons for every 10 to the 10 photons or so. So even if it's a tiny number, it's of course a very important number because it's the reason why we have matter and not just essentially photons around us. So the way that we think that this asymmetry could have been generated back in the early universe is that, so if we start with a universe that's symmetric, that contains the same number of baryons over anti-baryons, then there has to be some process by which a slight excess of baryons over anti-baryons is produced. And this is a very slight excess at this level of 10 to the minus 10 or so. But what happens later on is that all the baryons, all the baryon anti-baryon pairs will annihilate with each other, producing photons. And in the end, we'll only be left with this small excess of baryons over anti-baryons. And these are all the baryons that we see today around us. So already in the 1960s, Sakharov pointed out what are the three main conditions that are necessary in order for this step to occur, for this imbalance to appear between the number of baryons and anti-baryons. And those are a violation of C and CP, so both charge conjugation and the combination of charge conjugation and parity, departure from thermal equilibrium, and baryon number violation. So all these three conditions are necessary in order to generate this imbalance. In principle, these are all the three conditions that we need, but I'm going to argue that there is a way in which baryogenesis can occur without globally breaking the baryon number in the universe. And the main idea here is that if the baryon asymmetry that we observed in the visible sector is compensated by an equal anti-baryon asymmetry in the dark sector, or said otherwise, if dark matter contains an excess of anti-baryons, particles with negative baryon number over baryons in the same amount that we see happens in the visible sector, then the universe can be, taking into account these both fluids, can be overall symmetric, baryon number symmetric, but in the visible sector, we would see an effective excess of baryons over anti-baryons. And for example, this was proposed in this model of halogenesis and other similar models like the ones I'm going to discuss a bit later. So the main ingredient here is the existence of a dark antibaryon, so of a dark particle, a particle that's weakly interacting without the visible sector, but which carries a negative baryon number. So then in the early universe, when this baryon asymmetry is generated in the visible sector, at the same time, an anti-baryon asymmetry is generated in the dark matter sector. So at the same time that baryogenesis is proceeding, the production of dark matter is occurring. So this is a way in which we can connect the origin of baryogenesis and of dark matter. So now let's look at some very general properties or statements that we can make regarding what these dark baryons should look like. So the first thing that we have to be careful about is proton stability. So we know, as far as we can see, that the proton is stable on scales much longer than the life of the universe. So this means that processes like the decay of a proton into a dark baryon plus an electron should be essentially forbidden. The easiest way to forbid these processes is to forbid them kinematically. So therefore, we require the mass of these dark baryons to be larger than the difference between, for instance, for this process, the proton and the electron. And this essentially leads us to the condition that the dark baryon should be heavier than the proton. The other condition that we can make is related to how much dark matter is produced during this baryogenesis process. So if we assume, for instance, that the baryon number of the dark matter is -1, then the energy density in these dark antibaryons is just the same one as there is in the baryons, because for each baryon we have an antibaryon scaled by the ratio of the masses. So we know that we should not produce too much energy density in dark matter from these dark baryons, as much the greatest that we can have is the observed dark matter energy density. So therefore, we conclude that the maximum mass that these dark baryons could have is about 5 GeVs or so. So if they are exactly this mass, then all the dark matter would be made up by this component of dark antibaryons, and if it's smaller, it would be only a fraction of the dark matter content of the universe. So very generically, with this general reasoning, we can say that an interesting region or an interesting region of parameter space for these dark antibaryons would be between 1 GeV and 5 GeV. So GeV-scale and antibaryons. And these particles can be either fermions or bosons. In principle, we don't have any prejudice against any of the two. Of course, one can generalize this a bit more if one allows, for instance, for fractional values of the amount of baryon number that's carried by the dark sector particles, and then, for instance, with a mass of 0.7 GeV, if the dark baryons are carrying a third of baryon number unit, then one can reproduce the observed dark matter abundance in the universe. And analogously, if the baryon number of the dark particles would be larger than 1, then this would be modified a bit. But this is roughly the range of interesting masses that I'm going to be discussing.
So if chi is fermion, then you don't have P to chi E, right? But you're saying that they are similar process and
yes, that's right. So this process, for instance, would only be for a baryonic dark matter candidate, but we could have similar things. You could have a neutrino, for instance, also coming out, and then yeah, one could get a similar bound. Yeah, thanks. Okay, so far, this is what we can kind of say very generically about the mass of these dark baryons and the baryon number. And the next interesting thing, or the next thing that's interesting for us is to answer is how can these dark baryons interact with visible ones? So what are actually the ways how these interactions can happen? And this is something that we care about, for instance, for the purpose of trying to detect these dark baryons. So I'm going to split this into the possibilities that this dark baryon interacts with first, second, or third generation quarks, because the phenomenology for each of the cases is similar. So I'm going to start with the case with the assumption that these dark baryons may interact with first generation quarks, so up and down quarks. And the main phenomenological implication, or the main phenomenological application of this is on the Neutron lifetime. So let me very briefly review what kind of what we know experimentally about the Neutron lifetime. So there are two main ways in how we can measure the lifetime of the neutron. So the first one is the so-called bottle experiments. So these are just rely on like collecting a bunch of neutrons, putting them inside of a bottle. We know with how many neutrons we start with, and we let them decay. And we count how many neutrons we have as a function of time, and this should follow an exponential decay rate. And from this, we can obtain the Neutron lifetime from these experiments. Then the other kind of experiments are beam experiments. So in these experiments, what we have is a bunch of neutrons that are typically circling some storage ring or so. And what we do is that we measure how many protons are produced in the decays of the neutrons, because we know that in the standard model, neutrons decay via almost exclusively via beta decay, so they always produced a proton. So if we know with how many neutrons we start with, and we count the number of protons that are produced in these decays, we can also extract a value for the neutron lifetime from these experiments. So in the standard model, as I said, the branching ratio of neutrons into protons plus whatever is essentially 1. So this means that the lifetime that we expect be measured by these two experiments should be the same. However, this doesn't seem to be what experiments are finding. So here you have, as a function of the publication date, what value of the neutron lifetime is measured by different experiments. And you can see that systematically, the beam experiments seem to be finding larger values for the lifetimes than the bottle experiments. So experimentally, by now, there is about 4 sigma discrepancy in these measurements. So therefore, we can start thinking about possible explanations for this discrepancy. And perhaps the first thing that comes to mind is that, well, perhaps we were wrong in assuming that the only way that neutrons can decay is via beta decay. So there may be other decay processes or other decay channels for neutrons involving, for instance, dark baryonic particles like the ones we're studying that do not produce any protons. And therefore, this kind of decays will be counted in bottle experiments because, I mean, the neutron is disappearing in any case, but it's not counted by beam experiments because if no protons are produced, then these decays are not taken into account, are not counted when computing the lifetime in beam experiments. And actually, the discrepancy, the experimental discrepancy goes in the right way. That could be explained if there is a branching ratio of the neutrons decaying into anything that's not a proton of about 1%. So this opens the interesting possibility that in fact neutrons could be decaying into some dark baryons. There is, however, only a very narrow mass region for these final state products in these baryon decays, as I show here. So the upper value for this final state mass is of course limited by the mass, the kinematic requirement that the mass should be smaller than the neutron mass. I think this should be the other way around, of course. And on the lower end, we know that there are some nuclei like beryllium 9, which we observe to be stable. So we know that the neutrons within beryllium 9 are not decaying through this process too often. So therefore, we can place a lower bound, so we can block this decay kinematically as we did for the protons, and we find a slightly tighter bound in terms of in its numerical value than the one from proton stability, which amounts to this 938 MeV or so. So we see that there is only a range for about 1.5 MeVs in which this dark baryon mass should lie. Now, so looking into a bit more detail, what the possible decay channels are for the neutron to decay into dark baryonic particles, we have essentially these two possibilities, these two simple possibilities. The first one is that the neutron decays into just one dark baryonic particle, and also a photon is emitted in order for energy momentum conservation to be possible. So this is perhaps the simplest explanation, but it seems to be disfavored by data. So you see this blue line here. This is a function of the dark neutron mass and the neutron, so the dark baryon mass and the neutron dark baryon mixing, or the coupling between the neutron and the dark baryon. So we would need a mixing of this size, this blue line, to have a 1% branching ratio that would explain the anomaly. But there are some other experiments here in the shaded area that had excluded this possibility. So this one seems to be disfavored. However, there is another possibility. So if in the dark sector, we not only have this dark baryon chi, but we have some other states also carrying baryon number into which this chi can decay, then we can conserve energy and momentum without needing to emit a photon. So this would be a purely dark decay of the neutron, and that's something that's not constrained experimentally. So for this particle, so having a dark neutron of a mass of about 1 GeV, then as we will see some mediator with masses in the multi-TeV scale. I will discuss a bit more about this later on. And then some other, for instance, a fermionic and a scalar dark sector states whose masses are around 1 GeV or so, and whose baryon numbers add up to 1, then we can make this scenario viable phenomenologically and able to explain the neutron lifetime discrepancy. Okay, so this is relating just the decay of the neutron in terrestrial experiments, but we should actually worry about what happens to neutrons in astrophysical setups, and in particular in neutron stars, which are systems containing a large number of neutrons. So as we will see, these decays can be potentially very dangerous for neutron stars. So neutron stars essentially are systems of highly degenerate neutron matter in which the Fermi degeneracy pressure essentially of the neutrons are balancing the gravitational pull of all the matter in the stars. So an equilibrium is reached, which gives us the value for the radius of the star as a function of the mass of the star. However, if we now assume that the neutrons within the star can decay into these dark baryons, chis, what happens now is that these dark baryons will typically stay within the star. They will be gravitationally trapped, and they would still contribute to the gravitational pull in the star, but they would not contribute to the Fermi degeneracy pressure of the neutrons. So this means that as these decays accumulate, the star is losing its pressure support, and this can eventually lead to the collapse of the neutron star and the formation of a black hole for instance, in the most extreme cases. So this is something that people looked at carefully. And here, for instance, in this plot, you can see what the predictions are for the neutron star equation of state, so the relation between the mass of the star and the radius of the star for different values of the dark baryon masses. So this line here corresponds to the mass of some stars that we have, neutron stars that we have observed. So we know there exist stars with about 2 solar masses. But if there exists a dark baryon with a mass close, essentially equal to the mass of the neutron, like we need to solve the neutron lifetime anomaly, then it would not be possible for neutron stars to become as heavy because they would collapse earlier on. So the authors in this paper used this to argue that, of course, this depends slightly on the value of the mixing. If the decays are too slow, then this would not happen. But for the typical values for which we can explain the Newton lifetime anomaly, this would be very dangerous. So the authors here argued that the existence of neutron stars of 2 solar masses actually rules out the possible existence of dark baryons with a mass smaller than the neutron. And they could even argue that the results could maybe apply for even larger values of the mass, because even dark baryons heavier than the neutron could be produced inside of the neutron star because of the high chemical potential of the star. However, this now depends on the exact equations of state of the neutron stars, which is something that's still not so well known. So I would say that this is a robust exclusion, but for larger values of the masses, then we don't really know where this value lies exactly.
Sorry, can I ask? Maybe I missed it earlier on. Do the dark baryons have some other conserved quantum number associated with them? Well, why don't they annihilate with? Why don't these things which carry with negative baryon number? Why don't they annihilate with the regular baryons?
Well,
there is 100% particle antiparticle asymmetry, GeV. So.
Yes, it's only neutrons that are being produced. So here the neutrons are decaying into baryon numbers, into baryons, not antibaryons. So baryon number is conserved.
No, I understand the baryon number there is conserved, but your baryon asymmetry, I think you're saying, at least from what I got initially, you're saying that the net baryon number of the universe is still 0. It's just that some of it's in protons and neutrons, and the other is in this dark stuff.
I see. So what you're saying is that these baryons that are being produced in the neutron stars could annihilate with the dark baryons in the dark matter.
For example, I'm just wondering what prevents that.
I don't think anything prevents that, and I don't know if people have looked at this. One would need to compute what the cross section for the annihilation process is, and see if this can actually lead to the depletion of the neutrons fast enough. I mean, this would still potentially affect the equation of state, right? Because we're removing neutrons from the star. So I mean, I think that's an interesting question. It all boils down for what the annihilation cross section would be, I think.
But even in generating the baryon asymmetry, why don't the dark ones still annihilate with the normal ones?
So in the early universe, we assume that we produced only dark antibaryons, right? So
why don't they annihilate with the baryons, since there's just as many of them?
Well, I mean, as I said, I think one would need to look at what processes could happen and calculate the annihilation cross section. But I think it will be small enough for the values of the interaction rates that we have, in order for that not to be a problem.
Okay, so
yeah, so these dark baryons are still very weakly interacting with the standard model states.
Okay.
Okay. So I mean, but I think what you're proposing is perhaps an interesting thing to calculate. Right, say if these dark baryons produced in neutron stars could annihilate with the ambient dark baryons. Of course, if these bounds are independent of whether these dark antibaryons are the dark matter or not.
So does it affect this picture? Like, even if this chi particle, I saw that is just because you produce chi particles and they are not interacting with the neutrons at all. So that's why you lose the pressure and this collapse. And
yeah,
does that story is that story affected if you have some, I don't know, large annihilation cross section between the dark matter, Decay and anti-baryon in the dark sector?
Yeah, I think this is what Keith was also suggesting, and this could be modified. Yeah, so, and for instance, it could also be modified if the dark baryons have self interactions, or if the dark baryons have large interactions with neutrons. So this is what these people, for instance, have put forward.
Okay. I see. So it depends on the annihilation channel, right? So if this Chi particle and then dark matter just annihilates into some dark volume, and that are just escaping from this neutron star, then there's no change of the story. But okay.
Yeah. It depends on the exact model that then what we consider. Yeah. Good. Okay. Yeah. So there are definitely ways out, and people have suggested a few here. Okay, something else I wanted to mention is that there are some other constraints on dark baryons coming from astrophysics and cosmology. And I borrowed this very nice plot from a paper by Maxime and collaborators, where they were compiling a few of the cosmological and astrophysical bounds. So here, for instance, you can see again as a function of the dark baryon mass, and in the y-axis, the neutron dark baryon mixing. There's constraints. This is the one I discussed about beryllium stability, but then one gets constraints from Z and B, and also from BBN, the deuterium, I think, to hydrogen ratio. This depend on the values for the mass and the mixings. So there is interesting phenomenology here to explore also in astrophysics and cosmology. Okay, so now I want to move on to the interactions of baryons with third generation quarks. In this case, more focused on bottom quarks, and I'm going to be a bit brief because I want to get to the interaction with strange quarks. So here, what I find the most interesting is that if these dark baryons were to interact with bottom quarks, then there is a mechanism that in which I have worked together with some collaborators, in which we can actually find an implementation for how baryogenesis and dark matter may have been produced in the early universe. So this we call B-mesogenesis because it involves the dynamics of B-mesons, and I'm going to very quickly explain now how this works. So everything starts when in the early universe we assume that we have some long-lived scalar particles, S here, that decays at low temperatures, so temperatures of about 50 maybe MeV or so. And as long as this scalar has a mass larger than about 10 GeV or so, very generically, it will produce BB bar pairs. And at these low temperatures, the B quarks will quickly hadronize and form charged and neutral B-mesons before decaying. Because at these low temperatures, we would not expect to find essentially any B-mesons in the plasma. This population of B-mesons is out of equilibrium. So therefore, this satisfies one of the Sakharov conditions. So the next Sakharov conditions, which is CP violation, is actually very nicely supplied by the oscillations of neutral B-mesons. So we know that neutral B-mesons can change flavor, or also we say neutral B-mesons oscillate. And this is a process, as you can see here, that occurs within the standard model via these box diagrams in weak interactions. But the most interesting thing for us is that these neutral meson oscillations can be CP violating. And the condition for these oscillations to be CP violating is the following. So if the rate for a B-meson to oscillate into an anti-B-meson and they decay into some final state F is different to the rate for the charge conjugated process to occur. So the CP conjugated process, so the anti-B-meson oscillating into a B-meson and decaying into the CP conjugate final state, then there is CP violation in the oscillations and the decay of the B-mesons. And this quantity experimentally is something that we can measure at collider experiments, and it's called the semi-leptonic asymmetry, ASL, just because usually the final states that are used to measure this quantity are semi-leptonic final states, decays of the B-meson. So with this, we have the second ingredient, that's the CP violation. And the final ingredient, the baryon number violation, in line with what I discussed before, can be supplemented by the existence of a dark antibaryon. So if these dark antibaryons interact with B quarks, then the decay of a B quark inside the B meson can produce a dark antibaryon, and therefore decays like the ones in here, in which a B meson, so a state with baryon number 0, decays into a visible baryon, state with baryon number 1, and a dark antibaryon can occur. Therefore, we're generating a visible baryon asymmetry compensated by a dark baryon antibaryon asymmetry.
Sorry, can I ask
Yep.
a question here?
Sure.
So do you need extra CP violation in this model, right? Because otherwise you can't rely on CKM phases, right? Because that won't produce enough baryon asymmetry.
Yeah, so that's a good question. So typically so for instance, it's kind of common law that the CP violation in the standard model is not enough to generate baryogenesis, right?
Right.
But this is a statement that's true for instance, electroweak baryogenesis. But this is occurring at much lower temperatures where the CP violation in the CKM phase is less suppressed. So it's not immediate. So we have found that in practice, we need some extra CP violation. It's not enough with the one in the standard model, but it's not off by a lot. It's not off by orders of magnitude, like in
I see. So you're saying it's much closer.
So I have a related question. If you go to the early universe when the big quarks are, right, there is no confinement. So why do you even look at the B mesons?
So this is at low temperatures, 15 MeV.
Low temperatures.
Yeah, much.
And how do you source the B mesons?
Yeah, so the mesons are sourced by the decay. We assume that we have a long-lived scalar that decays late, like some scalar with a lifetime of 10 to the minus 3 seconds or so. That's the job.
I misunderstood.
Yeah.
So then the CP violation that you need, you're saying, is not that much compared to what's
not that
already
much.
there. I see.
And I think up to a few months ago, with some new measurements for these branching ratios, we thought that one could do with the standard model CP violation.
Oh, really?
So it's off, but just a factor of, say, a few.
Oh, wow. Okay. Yeah. Thanks.
Just because of the difference in temperatures. It's not like 100 GeV, but 15 MeV, which is occurring. Yeah, it would have been very nice if it were enough with the standard.
Yeah. No, definitely.
Yeah, but that's a good question. Okay, so yeah, I was here saying that now we have this dark baryon. Of course, for kinematic reasons, the mass of this dark baryon has to be smaller of about 0.3 GeV or so, because these decays have to be kinematically allowed. So something important to note is that this chi cannot be stable, because this chi can always decay back, for instance, into proton plus a pion, things like that. And the rates for these decays, if we want the rate for the B meson decay to be large, would be shorter than the lifetime of the universe. So this kind of decays would also erase the generated baryon asymmetry. So we have to assume that rather than decaying back into the standard model, these chi particles decay into further dark sectors. So this is similar to a dark sector, similar to the model that we need for the Neutron lifetime anomaly works here in this case. And it also makes it so that these other states, or at least one of them, can be stable and make up antibaryonic dark matter. Something also important to note is that these things cannot make up the full dark matter abundance, and this is related to this kinematic condition. So the mass of the dark sector particles cannot be larger than about 4 GeVs or so. So the amount of dark matter comes a bit shy of the energy density that we observe in the universe. So this would make a fraction of the dark matter, but cannot explain the whole of it.
Just to make sure, so here you really need a B meson on the D or K doesn't work just because of the kinematics, right?
That's right. So kaons are too light, and for D mesons, so Gilliel, or one of my collaborators, I think have tried to make this work, but I'm not too convinced that it actually works when one just because of the constraints that one has in the CP violation in the D meson sector. So for
I see.
B-mesons, this works because, as I'm going to say now, so the final baryon asymmetry essentially depends on two parameters related to B-meson physics. The first ones are the semi-leptonic asymmetries, so the amount of CP violation that these B-meson oscillations have. And so the values that we need here are values that are experimentally allowed. So with a semi-leptonic asymmetry at the level of 10 to the minus 4 or so, which is close to the one predicted by the standard model, one can make it work. I think the experimental limits on the semi-leptonic asymmetries are at the level of 10 to the minus 3. So there is room for new physics to come and enhance these semi-leptonic asymmetries. And the other quantity is this branching ratio for B-mesons to decay into a dark baryon plus a baryon and possibly some other mesons. And for a decay rate here for these values of 10 to the minus 4, we would need a decay rate at the level of 10 to the minus 2, which you would say is a huge branching ratio for B-mesons. How come that this is not constrained yet? But people have not looked for this kind of baryon or apparently baryon violating decays for the B-mesons. So there's room for branching ratios as large as 10 to the minus 2 or so as of now. But people are currently looking and to target these decays at LHCb and Bell. So we expect that with improved measurements in the semi-leptonic asymmetries and then searches for these exotic decay rates, the whole parameter space for our model will be tested in the next couple of years or so, which is, I would say, very exciting. Okay, so with this, I come to the last part of the talk, the one I wanted to focus a bit more on, and is the possibility that dark baryons interact with second generation quarks, and in particular with strange quarks. So this is what we looked at in the paper that I linked at the beginning, and this is why we refer, so we call this the strange physics of dark baryons. So before starting, I guess for those not too familiar with strange quarks, the hadronic states or the baryons that contain strange quarks are usually called hyperons. I will say hyperon a lot from now on in the talk. So for you to know what hyperons are just baryons containing strange quarks. So in the usual baryon octet here, where the neutron and proton lies. So these are the two states that do not contain any strange quarks. And there are another 6 states that do contain strange quarks. So we have the lambda hyperon, the sigma, charged and neutral hyperons, and the 2 chi, or sometimes called cascade baryons. And those are in general what we know as hyperons. So here you have, for instance, the different quark content of each of these states. Okay, so now we know what hyperons are. We want to study what we can say about hyperon physics if there were to exist dark baryonic particles. So as we saw, for the neutron decay and the B-meson decay, we have a very similar process by which the neutron and the B-meson could decay, and a very similar process, as we will see, also works for hyperon decays. So essentially, these decays are mediated always by an effective 4 fermion operator in which the dark baryon interacts with 3 quarks of different flavors. So here the color indices are not explicit, they are contracted in a completely antisymmetric way. And as we will see also the SU2 indices, so this can be left or right-handed quarks. There are 2 possible versions of this operator. And then, I mean, everything, what process can occur just depends on what's the exact flavor content of the US operator. So if we only have U and D quarks, then this leads to the decay of the neutron. If we have a mix of U, D, and S quarks, then we can have decays of hyperons. And for B-mesogenesis, as I said, we need to involve the bottom quark too. But essentially, the structure of the operator is always the same of this type. Of course, this 4 fermion operator is neither a UV complete model nor the best way to study hyperon decays. So we're going to be discussing a series of different Lagrangians. So we will start from a renormalizable model, essentially just introducing a mediator, either a scalar or vector mediator that mediates these effective for Fermi interactions and renders the model renormalizable. And then we will integrate out this heavy mediator in order to obtain the 4 fermion operator. But at the low energies in which we want to study not quarks, but hadrons as propagating degrees of freedom, we will need to construct a chiral effective field theory that describes the interactions directly between the dark baryons and the standard model hadrons. So let's start very quickly with the renormalizable model. As I said, it's very easy to UV complete this effective for Fermi interaction. One just need to add a scalar or vector mediator. So these are the 3 possibilities in terms of the quantum numbers of the states. So they have to be color triplets, so strongly interacting states, and then they can have hypercharges and SU2 charts as given here for the different implementations. But the most important thing is that these are colored particles. This means that they have to be sufficiently heavy, or otherwise we would have seen them at the LHC. So this means that the mass of these colored states typically has to lie above the GeV-scale or so that we can integrate them out easily for at the GeV-scale where the interesting hadronic processes are going to happen. So here you have the explicit Lagrangians. I'm not going to go too much into the detail. Essentially, you can, so these are just some Yukawa-like interactions between the different quarks. But let me instead very briefly mention.
Sorry, could I ask a question about the matter? So you've introduced a lot of colored matter here, is that right?
So I'm introducing, yeah.
Sorry, a lot of colored mediators, right?
Yeah, in principle, with one we can do.
Just one? Oh, I see. So these are just different versions.
Yes, yes. Sorry, I was not clear that. Thanks for the question. So these are just 3 possible UV completions, but it's like every one of them separately works.
Yeah, I was just wondering if QCD still remains asymptotically free with all this matter that you added, but the answer is yes, I think.
Yeah, yes, it is. It's just a scalar or a vector.
Yeah, you're not adding that much. Okay.
No, it's not that much. No, but thanks for this clarification. I think I was not clear. So it's not that we need the 3, but just one of them. Any of the 3. Yeah. So as I was saying, the main constraints actually come from searches for colored particles at the LHC. So typically SUSY-like searches. Again, I think I'll not go too much into the detail depending on what exact process. So production can be through non-resonant strong production or resonant QQY production. Then the limits on these particles range from mass of about 1 TeV or so, or masses between 1 and 7 TeV, depending on what the values of the couplings for these states are. So kind of a bound that summarizes the constraints is the one given here. So the product of the 2 couplings, so the 1 to 2 quarks and the 1 to a quark and a dark, and the dark antivariance, so this should be a chi, over the square root of the mass should be at the smaller than about 0.5 inverse TeV squared or so. So this is typical. So typical values for couplings of order 1s, LHC can constrain masses for these particles of a few TeVs. Another important thing is that these colored mediators can also modify neutral meson oscillations. So flavor mixing can be induced at 3 level or 1 loop. Of course, 3 level flavor mixing is dangerous. So it's potentially dangerous phenomenologically. So these kind of processes can probe masses for these mediators between 10 and 10 to the 5 TeV, so way beyond what LHC can do. But the caveat here is that the flavor mixing always depends on the product of 2 couplings with different flavor combinations. So for instance, here for kaon mixing, D S-bar mixing, we need a coupling to both D D and S, 2 different couplings, and this means that depending on what the structure of of the couplings of this heavy mediator, these bounds can be evaded altogether. So this depends now a bit on the flavor model building aspect of the model, but it's not kind of model independent constraint as the ones from the LHC are. So therefore, I will, even though this is potentially very interesting, it's not a complete strong model independent bound. Okay, so this is what I wanted to say about these colored mediators, because at the end of the day, we're going to be looking at dynamics occurring at the GeV-scale, and at those low scales, we're going to be able to integrate out this heavy mediator and write these effective 4 fermion operators down here. So now I'm making the color indices and the chiral indices explicit. So there are 2 versions of this operator involving only right-handed fields or both right and left-handed fields. So for hyperons, we want to focus on light quarks, U, D, and S. So in principle, we have this effective Lagrangian with these operators here with the right flavor combinations, so involving only U, D, and S quarks, and then these Wilson coefficients. And the size of these Wilson coefficients is given precisely by the product of couplings over the mass of the heavy mediator squared that's constrained by the LHC. So we know that these Wilson operators have to be smaller than about 0.5 inverse TV squared, as I was saying before, from LHC searches. So we have some handle in how large these effective operators can be, these effective Wilson coefficients can be, sorry. Okay, so the next step, as I was saying, is in studying the dynamics of hyperons, is to actually introduce hadrons and not quarks as propagating states. As occurs for energies below the QCD phase transitions, we don't have free quarks, but the propagating states are hadrons. So we need a theory where our degrees of freedom explicitly are hadrons and not quarks. And this is what chiral perturbation theory is. So chiral perturbation theory is based on the fact that without, for very light quarks, or so without quark masses, QCD is symmetric under SU3 transformations of left-handed and right-handed quarks separately. So it has this SU3 cross SU3 symmetry, which is quite well preserved, at least for the 3 lightest quarks, because the mass of the light quarks are much smaller than the QCD scale. Then chiral perturbation theory allows us to write an expansion of operators that respect this SU3 cross SU3 symmetry as a momentum expansion of the momentum P over the scale of chiral perturbation theory, so about 1 GeV or so. I'm not going to go into the details of how one constructs this theory, but the main features is that one can describe all the meson fields contained into this U, capital U field here, that depends on this phi matrix here that contains the light mesons, so pions, kaons, and eta mesons here. So this F is just a phenomenological parameter that's measured in experiments. We call it the pion decay constant. It's about 92 MeV or so. And the reason why we put all these different meson fields together in this form is that the matrix U constructed like this has a well-defined transformation properties under the symmetry of chiral perturbation theory, SU3 left cos SU3. So because the mesons are a combination of Q, a Q bar, then this U roughly transforms as a 3 and a 3 bar under SU3 left times SU3 right. But of course, we're also interested in baryons and not only in mesons. So we have to construct the make the analogous construction for baryons. This is a bit more tedious than for mesons, but one can construct this matrix that contains the light, the mesons, the baryons, sorry, in this octet, in this baryon octet containing neutron, proton, and the hyperons in this way. So the exact transformation properties of this matrix under SU3 left and SU3 right separately are a bit complicated, but of course, for the vector subgroup in which we rotate in the same way the left and the right-handed quarks, this B transforms as an octet under these SU3 vector transformations. So putting everything together, we can construct the Lagrangian or chiral perturbation theory describing the interactions of baryons and mesons. As I was saying, as a power counting expansion in momentum over the chiral perturbation theory scale here. So these are some power counting values for the different fields. Here, lowercase u is, so it's a combination of capital U. So this contains the meson fields in the appropriate way to make things SU3 cross SU3 invariant. So it's not too important what the form of this Lagrangian is, only that the three parameters that we have here are capital D and capital F, which are quantities that have been measured in experiment. So we have some, here you have some of the values that these parameters take. So now we have, with this, we have the theory that describes mesons and light mesons and light baryons. And what we want to do is to add the dark baryons to this chiral perturbation theory. So this turns out to be possible. And the reason for this is that the four fermion operators that we had describing the interaction between quarks and dark baryons have well-defined properties, transformation properties, under SU3 left cross SU3 right. So for instance, this left-handed operator here transforms for the left-handed field. So we have two left-handed quarks, so transforms as a 3 cross 3, and for the right-handed component just as a triplet. We know that 3 times 3 equals a 3 bar plus 6. But now, because of this antisymmetric tensor here in the color indices, only the fully antisymmetric irreducible representation 3 bar here survives. And this means that the left operator transforms as a 3 bar, as an anti-triplet under the left-handed transformation and as a triplet under the right-handed one. And similarly, one can calculate the same thing for the right-handed operator, and one finds that the transformation properties is the singlet under the left-handed transformation, of course, and as an octet under the right-handed one. So with this, what we can now do in order to obtain our effective chiral Lagrangian is to promote the Wilson coefficients that accompany these effective operators in the effective Lagrangian to spurions, transforming in the appropriate way so that the full effective Lagrangian becomes a SU3 cross SU3 invariant. So this means that these spurions have to transform as a 1,8 and a 3,3 bar. And with this, we can construct the most general Lagrangian at leading order in the momentum expansion, which looks like this. So again, these contain the baryon fields, the meson fields, and the dark baryon fields with these coefficients here. And we have, again, two possible phenomenological coefficients, alpha and beta in front. But these coefficients have actually been computed in lattice QCD. So we have, I mean, everything here in this Lagrangian is completely determined. So we can use this in order to obtain the rates for the baryon decay processes that we're interested in. So this is what I'm going to be discussing now. So I'll go a bit quickly. So this is the processes that we're interested in, the main decay rates that we identified as the most interesting phenomenologically. So the first is the decay of a hyperon into two dark sector states, so similar to the neutron one. Then also similar to the neutron decay, we have the decay of a baryon into a hyperon into a dark baryon plus a photon. And we have also this possibility in which the hyperon decays into a dark baryon plus light meson, a neutral or charged baryon. So this is for the lambda baryons, but similar things can be done for the other hyperons. So I'm going to go into the details. So the decay rates for these processes can just be computed from the Lagrangian that we have constructed. And essentially that results that we find factorize into three different pieces. So the first are the dependence on the UV parameters of the model. Essentially, this decay rate, of course, here you can see the diagram is going to be proportional to this effective coefficient for the four fermion interaction, and then also to this dark sector coupling of chi into these two further dark sector states. Then we have a piece that comes from the hadronic matrix element that we can calculate using chiral perturbation theory, and then also some kinematic factor depending on the masses of all the particles involved. So with this, we can make predictions for what these branching ratios for hyperon decays into dark sector states are as a function of the dark sector mass, mk. And here we've chosen the parameters in order to saturate the constraints from the LHC, so this 0.5 inverse TV squared that I had before, and then some particular choice for the dark sector masses. And we find that these decay rates, these dark decay rates of lambda and cascade baryons can actually be quite large, while still being phenomenologically allowed. So at the level of 10 to the minus 3 or even 10 to the minus 2 for some small regions of phase space. So this is for the fully dark decay. Then the other decay that I was mentioning before was the decay of a hyperon into a pion and a dark baryon. So here there are actually two terms, two Feynman diagrams that that contribute to this process. The first one is this kind of contact term in which the baryon just decays into a pion and a dark anti-baryon in this vertex. But we also have this pole term in which first the baryon transforms into the hyperon transforms into different hyperon by emitting a pion, and then this hyperon decays into the dark baryon. So because of this a bit more complicated structure, we have a bit more of phenomenology here. For instance, now the decay rates as a function of the mass depends on whether we have left-handed or right-handed operators. And now because, so of course, in this state, we could only deal, in the previous case, we could only deal with neutral baryons, but now we can have also charged hyperon decays. So here are the values. Again, we find decay rates which can be as large as 10 to the 4, 10 to the minus 3, without running into CMB, into the LHC constraints on the mediator.
Sorry, can I ask a question about the size of this this C coefficient? I mean, this is basically a mass that's around a TeV, right? Because it's a square root of 2. And so what happens if that scale is much, much heavier, right? Then what happens to these branching ratios?
Well, I mean, they would scale, as you can see here, as this coefficient square. So with the mass to the 4th power. So they become much smaller then. That's right. That's right. So you're taking the maximum possibility, which is that this particle is just around the corner. That's right. That's right. So this is the largest. Yeah, this is the largest you can get, because if these particles are really up at 100 TeV or 1000 TeV, then there's no chance. Much smaller. Yeah, for sure, for sure. But I mean, this highlights that we can have pretty sizable branching ratios for these processes. I'm not saying that this is the only possibility, of course. It could be much smaller, but they could be as large as this. I see. I see. Okay, thanks. Yeah, thanks. Okay. Yeah, and then for the final process, the one involving the radiative decay into a dark baryon and a photon. So, so this process can occur through a magnetic moment insertion here. And I guess the main thing or the main takeaway from here is that because we have this magnetic moment insertion, the rate would be suppressed by an extra factor of alpha electromagnetic. So we see that, as Tony was mentioning, for the largest possible values of the coefficients, we have branching ratios which are roughly 2 orders of magnitude smaller than for the previous processes. And this is just because of this alpha factor. Okay, so very nice. We have these predictions for some hyperon decay rates, but are they actually relevant for any experimental processes or any experiments? And the answer is yes. For instance, there are hyperon facilities that are studying the decays of hyperons with precision. One of them is BEST-3 in China, which is an electron-positron collider running at the GeV-scale pole, therefore producing, has currently produced about 10 to the 10 GeV-scale particles. And because these GeV-scale particles decay to hyperons with a branching ratio of about 10 to the minus 3, there have been about 10 to the 7 hyperons produced in BEST-3. So this means that one could even hope to prove branching ratios for these hyperons as small as 10 to the minus 7. In fact, there was a recent search for invisible decays of the lambda baryon, which found bounds at the level of a few times 10 to the minus 5. Of course, it's not quite 10 to the minus 7 because of experimental and tagging efficiencies, but it's still numbers for which we could actually have, which are at the level of 10 to the minus 5. So they're probing interesting region of parameter space. The other possibility is the LHCb, which on the plus side has even more hyperons than best 3. But on the minus side, we don't know what the initial state energy of our hyperons is. So this makes dark, so invisible searches, missing energy searches more challenging. But still, people are thinking about ways how to prove these dark baryons in big hadron decays and perhaps also in strange hadron decays. And another thing, I'm going to go very quickly because I think I'm already over time, that's relevant, is the fact that hyperons exist in supernova explosions. So in the proton-neutron star, proton-neutron star that's generated in a core collapse supernova, there are actually, depending on what the exact model is, but potentially a sizable number of hyperons, so up to so this fraction of hyperons over the total baryon number, as large as 10 to the as large as 10%, or 1% for different models. And this means that if these hyperons are decaying invisibly inside the proton-neutron star, this can lead to an anomalous cooling of the star, and therefore can have phenomenologically relevant effects. So one thing, I guess this is similar to the bounds that people placed on weakly interacting particles like axions. The main difference that we found here is that because we're producing GeV-scale particles, gravitational trapping is something that becomes very important. So because we're producing heavy particles, typically the kinetic energy that these dark baryons have when produced in the star is not too large, and therefore it may not be enough to actually escape the star. So they would stay within the star, possibly be reabsorbed. So only a fraction of the dark baryons produced leave the star, and this is important to calculate the cooling rates. So I'll go quickly, but if you have more questions, I'll be happy to discuss it. So now what we did to get bounds based on the supernova 1987A, whose neutrino burst was observed at Super Kamiokande, is to use what's sometimes called the Raffel criterion. And this is just demanding that the luminosity in these dark particles, these dark baryons that are produced inside the star and leave the star, cannot be larger than the neutrino luminosity. So we used some state-of-the-art supernova simulations with this particular equation of state, and introduced hyperons and hyperons decaying into dark baryons into these simulations, and found the bounds that you can see here in this plot. So the first thing that you can see is that the supernova 1987A can probe branching ratios which are orders of magnitude smaller than what we can currently probe at collider experiments. For instance, this is the a few times 10 to the minus 5 limit placed by BESS3. And you can see that with supernova 1987A, we can go as low as 10 to the minus 9, branching ratios much tinier than this. So this is for purely invisible decays. For visible decays involving pions, the bounds are a bit weaker, but still orders of magnitude below what we think could be done at hyperon facilities. So then what are the prospects for hyperon facilities if we've seen that supernovae place such strong bounds on these decays? So here is what I try to summarize in this table. So let me very quickly get you through it. So here in the first column, you have the initial state hyperon that's decaying via the channel shown in the second column. And this is just the possible maximum mass for the dark baryon that can occur in this decay, the operator through which the decay happens. And this is the maximum branching ratios that we have calculated in chiral perturbation theory in light of the constraints from the LHC on the mediators. So we see they're at the level of 10 to the minus 3 or so, or a bit smaller. And these are the bounds coming from supernova 1987A. So as you can see, these are orders of magnitude smaller than what we could, and therefore this means that for many channels, we would not expect to see something visible at any hyperon facility. However, there are two caveats. The first one is that cascade baryons are not constrained by supernova 1987A, and they can have branching ratios as large as 10 to the minus 3. So here there is a good opportunity for hyperon facilities to focus on this kind of hyperons. And the other one is that sigmas are less constrained by the supernova. So these bounds are only at the level of 10 to the minus 4 or so. So there is potentially also some region to be explored at terrestrial experiments. With this, I want to finish. Sorry for going a bit over time. So the summary is that GeV-scale dark baryons are what I think a well-motivated extension of the standard model based on arguments, the fact that they could explain both dark matter and baryogenesis. And they can couple, and they have an interesting phenomenology depending on what generation of quarks they couple to. So first generation quarks, we have possible effects on the neutron lifetime and interesting cosmological and astrophysical consequences for third generation quarks. I've shown a particular model that implements the production of dark matter and baryogenesis in the early universe via B-meson oscillations. And for second generation quarks, we have hyperon decays, for which we have made predictions for terrestrial experiments like BESS-3 and the LHCb using chiral perturbation theory. And finally, we have seen that supernova 1987A, including gravitational trapping, can place strong constraints on these decays. And with this, I finish. So thank you very much for your attention.
Thank you, Gonzalo, for the nice talk. So, are there any questions?
So, these branching ratios that you have, even at the level of 10 to the minus 3, seem large to me. You know, for lambdas and sigmas, you know, the decay channels are extremely well measured. And especially if you say, you know, a lambda with a pion in the final state, I'm surprised that you could have anything as large as 10 to the minus 3. I would have thought that that just the experimental limits on any kind of, you know, non-standard decay would be much smaller than that.
So we were looking a bit into that to see if there are some kind of inclusive processes that we could use, but we didn't find constraints at this level for, especially for these decays with missing energy, because so in most of the experiments, so you try to reconstruct the full decay, so you're not looking for missing energy states. And actually something that also becomes important is that, so for instance, in these hyperon decays, you could also have neutrons, and neutrons are essentially missing energy for many detectors, right? So for instance, this decay, so in the standard model, we could have a decay of lambda into a neutron plus apply 0, and we could not distinguish between the decay of into a neutron plus apply 0 and into a dark baryon plus apply 0. So there is, so that's a good point, but I think these kind of branching ratios are still experimentally allowed. But I think that the experiments should be able to play tight bounds, as is exemplified by this search here. Which
I mean, 10 to the minus 5, you know, maybe more of what I expected, even maybe even less than that. You know, it's just when you look at the known decay channels, you know, they essentially add up to very close to 100%. So now, question, you know, of course, the level of 1.1 times 10 to the minus 3, if you subtract that, that's still almost 100%. But but when you start looking, you know, these. You know, the dominant two modes, right? Just for pions and nucleons is, I'm just looking at it now, is 99.7%. And then you add, you know, the other ones that are measured, and you essentially, you know, you add them up and you get, you know, almost 100%. So, and then if you're now saying, as you said, you're looking for specific inclusive processes where you know there's a pion in the final state, I would have just expected much smaller, you know, much tighter limits on the branching ratios, but, you know, maybe nobody's done it. So
I think it's an exercise worth doing it. So we haven't done it for hyperon decays, but we did it for B-meson decays, because there I was also talking about branching ratios at the 10 to the minus 2, 10 to the minus 3 level. We thought there's no way this is possible, but we found that so when we looked into the detail at the known branching ratios, we found that so decay rates at the 10 to the minus 2 or 10 to the minus 3 level containing missing energy were still allowed. And as I was saying, the main things were, the fact that these inclusive channels sometimes so contain neutrons, and it's very hard to distinguish between neutrons and missing energy. So one could very easily think that, my B-meson has decayed into a neutron, but it was actually not a neutron, but a dark particle. So even for B-mesons, we could not play this game to constrain the branching ratios below the 10 to the minus 2 level or so. Perhaps for hypernons one can do it, but I have not looked at the Lammers into the detail in detail. But that's a good point.
Any other questions? So, okay. So you mentioned the neutron lifetime anomaly and B-mesogenesis, but is there any kind of Pheno motivation to think about these couplings to the second generation quarks? Like you mentioned D-mesogenesis, but you said that you are not convinced, right?
I'm not too convinced by those models. I guess the main motivation is, so if one is like in a full, once you construct this model, you need a full flavor model, right? So unless you have some symmetry that's forbidding some couplings, in general, I would not expect the dark baryons to couple to just a single generation, right? In principle, one should just consider some flavor model, either a flavor universal or flavor, I don't know, some sort of minimal flavor violation setup, and then look for those bounds. And then I think in practice, the other thing why it's interesting to do so is that, as I was saying, with flavor, with meson mixing, you can place constraints on the couplings of different to different quarks. And now, if you put that together, so say if I can constrain from B-meson mixing the coupling to B's and S, and then I can constrain independently from hyperon decays the coupling to S, then I'm constraining the coupling to B's too. So the goal is to kind of not look generation by generation independently, but at the end have a global view for, say, just write the couplings of the dark baryon in to any plausible flavors and get a global view.
Yeah. So I guess in that case, as you mentioned, not only the hyperon decay, but also the mixing between or flavor changing process will be important, right?
Yes, they are very important. So I have not covered them into detail because I do not have much time, but there is rich phenomenology there too.
Okay. Any other questions? Yeah. If not, I can stop the recording. And thanks again, Gonzalo, for the nice talk.
Oh, thank you very much.